Hello. Hello and welcome to this video of PostgreSQL functions and operators. In this video, we will finish the remainder of binary string conversion functions, and we will also go through bit string functions and operators. This will be a relatively small video because there is not much to cover. However, pattern matching, which will be the next topic after bit string functions, is a large one, and we will take some time to cover it. And pattern matching is a bit complicated as well. So we had stopped before 9.13 table, and we will look what functions it offers. So the description says functions for converting strings between different character sets, which are also called encodings, and for representing arbitrary binary data in textual form are shown in table 9.13. For these functions, an argument or result of type text is expressed in the database's default encoding, while arguments or results of type byte array are in an encoding named by another argument. So we have convert function, which takes a bytes input, a source encoding name, and a destination encoding name. So it will convert the byte array from the source encoding to the destination encoding. For example, this is a text in UTF-8 with underscores, and UTF-8 encoding is converted to Latin 1 encoding like this. So like other functions, we can run this directly on Postgres. You can say select and paste it, and there you have the converted stuff. Then you have convert from, and you have bytes argument, which is a byte array argument, and then source encoding name. It converts a binary string representing text to in encoding, source encoding to text in the database encoding, which would be mostly, if you don't change the database encoding, it will be UTF-8. So it will convert text in UTF-8 to UTF-8. So for example, if you want to see what happens to it, it will remain unchanged because database encoding is UTF-8. Then we have converts to, which will take a string argument and convert according to destination encoding. Converts a text in string in the database encoding to a binary string encoding and encoding destination encoding. Then we have encode, which takes a bytes argument and a format argument and converts it to text. Encodes binary data into textual representation. Supported format values are base 64, escape, and hex. Then we have decode. Decodes binary data from a textual representation. Supports format values are same as for encode. So format can be base 64, escape, or hex. For example, this is a base 64 string, and you can decode it to give you byte array as the output. The encode and decode functions support the following format: base 64. This format is that of RFC 2045. As per the RFC, encoded lines are broken at 76 characters. However, instead of the mine CRLF end of line marker, only a new line is used for end of line. That is Unix style and not Windows style. The decode function ignores carry return, union space, and tab characters. Otherwise, an error is raised when decode is supplied invalid base 64 data, including when trailing padding is incorrect. Then we have escape format. It converts 0 bytes and bytes with the high bit set into octal escape sequences, and it doubles backslashes. Other byte values are represented literally. The decode function will raise an error if a backslash is not followed by either a second backslash or 3 octal digits. It accepts other byte values unchanged. Hex. The hex format represents each 4 bits of data as one hexadecimal digit 0 through F, writing the higher order digit of each byte first. The encode function outputs the 8 through F hex digits in lowercase. Because the smallest unit of data is 8 bits, there are always an even number of characters returned by encode. The decode function accepts the A through F characters in either upper or lower case. An error is raised when decode is given in invalid hex data, including when given an odd number of characters. In addition, it is possible to cast integral values to and from type byte array. Casting an integer to byte array produces 2, 4, or 8 bytes depending on the width of the integer type. The result is a 2's complement representation of the integer with the most significant byte first. So for example, if you cast 1, 2, 3, 4 small int to byte array, you get 0, 4, D2. And similarly, you can look at other examples. Casting a byte array to an integer will raise an error if the length of the byte array exceeds the width of the integer type. So we now move on to bit string functions and operators. This section describes functions and operators for examining and manipulating bit strings, that is, values of the type bit and bit variant. While only type bit is mentioned in these labels, values of type bit variant can be used interchangeably. Bit string supports the usual comparison operators shown in table 9.1 as well as operators shown in table 9.14. So we have concatenation operator, which we have already seen. So it takes 2 bit strings and outputs another bit string of concatenation. Then we have bitwise AND, which will perform the AND gate, that is true for both bits being 1, false otherwise. Then we have bitwise OR, which will output 0 for both being 0, both inputs being 0 and 1 otherwise. Then we have exclusive OR, which is represented by hash, which will be 1 if both inputs are opposite or 0 otherwise. Then we have bitwise NOT gate, which will flip the bits, and shift, left shift is there, which shifts the bits to the left side, and we have the right shift, which shifts the bits to the right side. Now we look at the bit string functions. We have bit count. So it counts the number of set bits in the bit string. Bit length will return the number of bits in the bit string. Length will return the number of bits in the bit string. So length or bit length will give you the same output. Then we have octet length, returns the number of bytes in the bit string. Then we have overlay, which takes a bits argument, and it is like other overlay. So there is a new new substring argument also there from start, which is an integer, for count, which is another integer. So it replaces the bit substring of bits that starts at the started bit and extends for count bits with new substring. So for example, if we look from 2 for 3, so it would be these 3 bits, and we will place there 5 ones. So that is your output. Then we have position, which takes substring and bits as 2 arguments, and it returns an integer, which is the first starting index of the specified substring within bits, or 0 if it is not present. Then we have substring, which takes bits argument, which is a bit string. Optionally, it takes a start integer and count integer. It extracts the substring of bits starting at the started bit if that is specified, and stopping after count bits if that is specified. Provide at least one of start and count. So here from 3 for 2. So third is this and 2 bits are this. So it will extract 0, 0. Then we have get bit, which takes a bit string and an integer. So it extracts the nth bit from the bit string. The first bit is bit 0. So this is a special thing you need to know, that this is 0 indexed here. Set bit takes a bits bin string and integer and new value for that new value as another integer. So sets the nth bit in the bit string to new value. The first bit is bit 0. In addition, it is possible to cast integral values to and from type bit. Casting an integer to bit n copies the rightmost n bits Casting an integer to the bit string width wider than an integer itself will sign extend on the left. So, for example, if you cast 44 to 10 bits length, it will become this much. So, if bit string is wider, it will pad with 0 on the left side. If you cast 44 to 3-bit string, then rightmost 3 bits are 100. Then if you cast minus 44 to bit string of 12, it will be this much. And if you cast 1110 bit string of length 4 to integer, it will become 14. Note that casting to just bit means casting to bit 1, and so will deliver only the least significant bit of the integer. So you can play with these functions and try with the various inputs to get a hang of it and reinforce your memory and understanding. So we will stop here, and in the next video we will look at pattern matching, and I will try to bring some extra examples for pattern matching for this particular topic. So it will be quite big. It is roughly 19 pages. So there is regular expressions involved. Pattern matching will contain regular expressions, and there are lots of examples already given in this. And then we have details of regular expressions and everything. So it will take a while to actually finish this. And 9.7. So there is quite a bit of information here. So I don't know how many videos it will take, maybe 3 or 4 videos it will take. So we'll see how much time it takes. I hope that you're enjoying this playlist of SQL with PostgreSQL. And once we are through with functions and operators, we will go back to practical of the SQL queries. And we will do a lot of examples, and then we will move on to indexes, full text search, and perhaps parallel query and all that. And no, parallel query, before parallel query, we will do PL SQL stuff, and we will cover chapter 41 for this. And then we need to study triggers, event triggers, and all that. So I thank you for watching the video, and keep learning. It is not necessary to watch the video for information. You can go ahead and read the documentation yourself. And if you have any questions on the material which I have covered till now from the playlist, you can go ahead and ask. And if you have any other questions from the documentation, please do ask me by making use of the comment box, and I'll try my best to answer your query. So once again, thanks a lot for watching the video, and I'll see you in the next one. Till then, ciao.